So everything on the computer, from the very base all the way to the very top, you can be thought of as they kind of get something that works, and then they encapsulate it and treat it like a black box, where there's input and there's output. And if you open up that black box, you would find other things inside there that's broken up in different pieces. Each one of them treated like a black box, where there's input and there's output. And then if you even go farther outward, this chip right here is itself obviously a black box with beams parts out of it. But then that's part of the motherboard, which has, you could think of the black box of the CPU, the black box of the network card, the black box of the sound card, the video card, okay? The black box of the USB ports and terminals that control where they controls that. And if you can dig inside there and see what they look like, and you can go farther and farther and farther down. Or you can go even to the part where you zoom all the way back out, and literally it's a box, a black box, the whole computer, where you've got inputs like USB, the keyboard, the mouse, and you have outputs like the speakers, printers, and the monitor. You see what I'm saying? Everything on all levels of viewing it look like that, and that's one of the big principles. If we zoom in on the CPU, some of the things that you see are something called the ALU, the Arithmetic Logic Unit. Also, the CU, the Control Unit. Okay. Also, even on here, there is some RAM. There's cache. There's ROM, which is where your firmware is going to be. Okay. And if we were to actually look at what this looks like, it's like a wire, and there's things going on, and there's wires here, and then they come out here, and then this wire here, and this wire here, and this wire here, and they meet, and they do this, and it comes out there, and there's this wire, and there's wires here, there's wires here, there's wires. Okay, so you get the idea. It's just like crazy amount of wires, connections, and stuff like that. Okay. Where two wires meet, or where three wires meet, one of those things is yet another black box called a logic gate. Okay? I should kind of look at those things. You also have groupings of logic gates. Like there's an intermediate level between these. You get things like multiplexers, adders, buses, demultiplexers, buffers, so on and so forth. Okay? So there's groupings there. Anyway, so then eventually at some point there you have these things called a logic gate. All right? Now, the logic gate and other items, if you were to break it down, okay, you would find transistors and resistors and diodes, okay, maybe a capacitor. You'll learn about resistors and capacitors, maybe diodes in your physics class, okay? But these are we're getting really, really close to just the straight wire and the this is not the semiconductor, the semiconductor material, okay? So we're getting real close. The big one that I'm going to focus in on is the transistor, because you can think of the logic gates as made up of a bunch of transistors.
Sadie Davis, please come to the office. Sadie Davis.
A transistor fundamentally does one of two things. It either amplifies a signal or it acts like a switch. What we're going to be focusing in on is how it works like a switch. Come on in. It's not a switch. I've already been recording, so you can get caught up here when you watch the video, okay? But the bottom line is we're zooming in on the CPU. It's got parts of the CPU, bunches of wires. These wires are meeting together in things called logic gates, which can be made up of these things. One of those things is called a transistor, okay? So a bunch of transistors will make logic gates. A bunch of logic gates will make up your ALU, your control unit, RAM, ROM, cache, stuff like that. That's part of your CPU, which is then connected to your computer, okay? So let me tell you about a transistor and kind of show you how it works without giving you a full physics lesson or digital or electronics lesson. So here we go. So a transistor, you can think of it like a black box, all right? But we're going to draw it like this. normally it's this thing that's in the circle. Man, I'm gonna draw the circle right there. Okay. So a transistor normally has 2 inputs. 5 volts of electricity right here. Okay, so you can think of this as like power available for you. Okay, there's a bunch of electrons that are free up here that they can start traveling down here. And then you have your input voltage, which is another location where you might send some electrons through here, or you might not. That's your call. And then over here we have a wire. This is our output wire. We're calling it V out. Okay? And the way that this works is really simple. This is providing power to the transistor. But these electrons, they all want to flow eventually down here to ground. Okay, this thing is a resistor, but we're not going to worry about that. They all want to flow. But this voltage right here is providing the gateway. It's essentially a switch. If this is turned on, if there's voltage here, then this current will flow, and I will get an output value of I'll be able to read voltage here. I'll be able to read power. It's voltage, not power, but you'll be able to, as these electrons are flowing and they come across this resistor, it creates what's called a voltage drop. But you can just imagine it like water. That right here we're looking to see if the water, if there's any water flowing. Okay, and if this says yep, if this says, if we put 5 volts here, okay, which I'll represent with a 1, then it opens the gates, the current flows, and when we're looking at here, we see current flowing, and we're like, yep, we get a 1. And if I press 0, or if I send 0 volts here, that effectively shuts the gate, and all of the water comes here and just stops. And so then we look at this voltage output here, or we look and see, nope, there's no water flowing, there's no electrons, and so it's 0. You're like, that seems kind of silly. Why don't we just look and see whatever this one is? Right? Because then there's a match. Just there's a reason why. Okay? And so what this acts like is a digital switch. It's literally up or down. Only instead of mechanically getting the switch and moving it with the force of your hand up and down, you're turning it up and down with voltage, with electricity. It's electricity controlling electricity. Okay? Now, you say, big deal. Well, let me show you what happens when you put 2 transistors together in a special way. Okay? This is A, and this is B. And this is plus 5 volts. And this is an arrow, by the way. And right here, I have V out. So, think through this with me here, folks. If I have no voltage here and no voltage here, okay, is the current going to be able to go through here? Nope. So if I put essentially a 0 volt here and 0 volt here, then V out's going to get 0. What's going to happen if A stays 0, but B, I flip the switch and turn it on?
Come to the office, please. Sadie Davis.
It's still going to be a 0 over here, okay? Because nothing's there's nothing available right here. See where we're going? What if I turn A on, but B is turned off? It's going to flow all the way up to right here, but it's not going to flow through the B transistor. Okay? The only way that I'm going to get any current going through here is if both of those transistors are turned on. Okay? Now, what sort of relationship does that look like to you? Or two things have to be true in order for the output to be true. Looks like an AND gate. Looks like an and, right? And this, they put a black box around all of it. And they don't even tell you about the power volts. But this is what's called an AND gate. And this is how they make it. They get a transistor, another transistor, they power it, send it to power, they connect the wires so that the input and the output are lined up like that. These are actually called emitters and collectors, and that's not really important right now. But then you have an output. They put a black box around it, and they say, boom, there's an AND gate, okay? And they don't draw it like this because we don't need to know all those details. You didn't need to know all those details. This is how they draw it. They say A, B, those are the inputs. Then they draw this like sort of semicircle type thing with a bar there, and then they have the output. And that output, sometimes they'll write it as AB with just the two letters right next to each other. This is the mathematical expression way. Sometimes they'll say A times B, where that means and. The times means and. Sometimes they'll write it as A and then this little guy right here, B. Or they'll write it as A intersection with B. Right? And that's called an AND gate, and that's what's going on at the electronic level. We could, if we wanted to, buy 2N22 transistors, okay? And I could put them in a little particle board. I think in my engineering class, hopefully we will. And we could put them in the board, and we could wire them there, put plus 5 volts, plus 5, and we could turn this up and down, and turn this, 5 volts here, 5 volts there, and we would see this exact pattern. I have a demonstration of it, but that would just take too long. I think y'all can take my word for this. If this is beginning to intrigue you, okay, this is what electrical engineers deal with, okay? You take 4 years of college and you end up learning how everything goes, even lower level than this. You actually learn in your physics class what's going on, in your materials class, what's going on with the chemicals right here. Why does it allow this? Which way are the electrons going, and why do they do that kind of stuff? You learn that in physics. And you just and you build from here all the way up, all the way to a computer. Okay? These guys are looking at our interesting symbol I'm drawing here. Okay? Now, that's not transistors. When they found out how to make these suckers, okay, it knocked the doors wide open. So much stuff was able to fit. Now, before they used transistors, they used these things called vacuum tubes, which would work the same way, but they weren't as easy to make. Okay? And they would kind of burn out and stuff like that, and there were some problems. But transistors, they could use, using semiconductors, use silicon, and it was a really fast, easy way. Let me show you another way that you could wire something. So we've got plus 5 volts. Sometimes it'll be 6 volts, but that's not really important right now. Comes down here, and it goes right there. Then we've got, that's your A input. Then you have your B input, just a straight line there. And this 5 volts pops over like that. And then from here, we go through resistor ground. This is our V out. Alright, so just start counting binary 0, 0. If I put 0 volts here and 0 volts here, notice nothing's traveling through this gate, nothing's traveling through this gate, and our V out is going to be 0. However, if I put a 1, if I put voltage on the B, that's going to open up this gate. Alright? And what's different here is that my power is directly connected to that gate. Okay? My 5 volts. So it's going to start to flow. And as it flows, it'll then flow through the resistor. And this V out, when it looks here, it says, is there water flowing or electrons going? Yeah, absolutely. There is. So it's going to see, it'll register positive voltage there, which is a 1. if I shut that gate off, but I turn this one on, I send power here, now I've got 5 volts coming down through here, hopping, going underneath the tunnel, and then right here, and they're flowing all the way down to the ground. I'm also going to read 1 volt there. And of course, if they are both on, then yeah, I'm going to receive voltage there. Now, what does this look like that you've seen before, this sort of diagram?
OR gate.
It's an OR gate. So what they do is they do the same thing. They box this whole thing up, and they call it an OR gate. And they have a special symbol for that. It looks even more obscene. If that's not obscene, just anatomical. So anyway, that's the picture that they draw. They say, this right here is an OR gate, because quite frankly, you don't need to know what's going on inside there. You don't need to know that there's a transistor and transistor. You don't need to know if it's BJN transistors, NPN transistors, MOSFET transistors, vacuum tube transistors. You don't need to know about the details. This is all you need to know, okay? And the way that they write that in symbols is A plus B. Plus means OR. So also, or another way, they write it as an upside down caret, or as a union. That's not, that looks more like a, it's like the actual official union sign, like that, in contrast to the intersection sign there. Alright? And so that's how you get an OR gate. Another one that you get, transistor-wise, this is the last transistor diagram I'm going to show you. After that, I'm just going to show you the shortcuts. So we've got 5 volts there. And so A and B out. If you have 0 volts here, then this starts to flow, okay? Or it doesn't flow rather, and V out is just showing 5 volts, which is 1. And then if you put voltage on here, and all this starts to flow, well, we would need to have a resistor down here for it actually to register. So the thing is that everything flows by so fast that essentially you don't see any voltage at all, and it turns into 0. What does that look like?
Not.
It's a knot. It's also called an inverter, but we'll call it a knot gate. We'll call it both, since that's what it is. And the symbol for that is a triangle with a dot on the end. So if this is A, we would write that as A with a bar over it, which is not A. Okay, so far so good. And there's more. I'm not going to draw the transistor diagrams for all these. I'm just going to draw for you the logic diagram and the truth table. Okay? So we also have something called a NAND gate, which is short for not AND. So it looks like just a regular AND gate, but with a circle on the end. So you'd have A, and here you have B, and here you would have not AB, not A and B. The truth table is exactly what you would get is if you were to say A and B not. So 0 and 0 is 0. Not, it's 1. Make sense? Okay. 0 and 1 is 0. Not makes it 1. 1 and 0 is 0. Not 1. 1 and 1 is 1. Not makes it 0. And there's a NOR, which looks exactly like an OR, but there's a circle on the end. And that would look like A or B not. So what's, say it out loud to me, folks. 0 or 0?
0.
Not?
Not 1.
1, okay? So 0 or 1. You just say 1.
1.
Not
0.
1 or 0.
0. Or 1. Sorry, 1.
1. Not 1 or 1.
1.
Not
0.
Okay? And that's where we're going to stop. Thursday, we'll pick up and finish doing this, as well as do some practice problems. I'm going to give these to you, though, just so you've got a copy of it, unless you are afraid you're going to lose it. Think you can hold on to that till Thursday?
Yeah.
Is Thursday a possibility?
That's when we're gonna go help Mr. Stanford.
Okay.
Well, I'm pretty sure because I see maybe that we're on the road.
That's fine. Well, I'll record it, and then you guys can watch it. These are the type of questions that you're going to see on that UIL multiple choice section. Okay? So, all right.
Oh,